Welcome. So, over last few weeks we have been discussing over iterative solvers. We started our initial discussion for the basic iterative solvers like Jacobi, Gauss-Seidel, SOR. What we have observed there is that the basic iterative solver, that is these class of solvers, they are only valid for diagonally dominant or irreducibly diagonally dominant matrices. Another thing what we have observed, that the rate of convergence for these solvers, that is Jacobi, SOR, Gauss-Seidel, this class of solvers, different version of symmetric SOR and etcetera are also there. So, the rate of convergence of this class of solvers depends on the spectral radius of the iteration matrix G, and SOR can probably give us best convergence rate for the optimum over relaxation factor. Now, the two limitations that we can notice out of basic iterative solvers. By the term basic iterative solvers will mean Jacobi type of solvers. That one, as we discussed, they are not applicable for any non-singular matrix. The matrix has to be diagonally dominant or irreducibly diagonally dominant. And if I take a diagonally dominant matrix and then if I do a row permutation on that, I will still end up in a matrix which will not remain a diagonally dominant matrix and which cannot be solved by Jacobi type of solvers. The matrix A probably can be solved by Jacobi type of solvers, but when I do row permutation, it does not remain diagonally dominant, though the solutions essentially remain same, it cannot be solved by Jacobi type of solvers. This is a very strong drawback of these methods. Or I will not say drawback, but limitation of these methods. The other one is that the convergence rate cannot be improved beyond what I am getting for optimum SOR parameter in successive over relaxation method. So, we started looking into other types of iterations, and we saw that the gradient search method or steepest descent type of algorithms can be another way of solution of solving X is equal to B iteratively, where we do not directly iterate for the solution vector X, rather we try to minimize a functional like B minus X or L2 norm or something. And then we realized that this method is basically something like a projection method, where we update our solution vector along a particular vector in each iteration, and the residual remains perpendicular to another vector. Now, using this we have demonstrated few methods. One is steepest descent algorithm, which now can be utilized only for symmetric positive definite matrices. So, the restriction, instead of keeping it as a diagonally dominant or irreducibly diagonally dominant matrix for basic iterative solvers, for steepest descent will be symmetric positive definite matrices. Now, if we come to the other variants of this projection based methods, we get minimum residual method, which can be utilized for any positive definite matrix, and residue norm method, which can be utilized for any non singular matrix. And then in last couple of classes we have discussed that how we can write programs, computer programs for basic iterative methods like Jacobi type of solvers, and also for the projection based solvers like these things steepest descent or minimum residual or residue norm. So, what we will start today, we will see how are the performance of these methods, and we will see that if this projection based concept can be developed further to get a much faster iterative solver, which is also applicable for wider class of matrices. What we will do today is, or what we will start from now onwards, is Krylov subspace methods. Krylov was a Russian mathematician who has identified a particular vector subspace, and later it has been explored that these subspaces can be very well utilized to develop efficient matrix solvers. So, we will start our discussion on Krylov subspace methods. We will go through Arnoldi's method, full orthogonal method and Langs's method, especially in this week we will do so, and later we will see that how much better matrix algorithms can be developed using this. So, let us look into performance of different iterative methods, and what we are doing, we are using the computer programs that we have discussed over last few classes. So, we took a 1000 by 1000 matrix, which is diagonally dominant symmetric matrix coming from a finite difference approximation in a 3D geometry, and we see the number of iterations using Gauss Seidel with successive over relaxation and steepest descent, and we use an over relaxation factor which is close to the optimum over relaxation factor, and do a numerical analysis to find out the optimum over relaxation factor, but by numerical experiments we find something we are getting the best convergence rate. So, if I use GSSOR for this matrix, we get that in 74 iterations the solution converge, whereas steepest descent, this is a symmetric positive definite matrix, but steepest descent is much slower, it takes 292 iterations. Now, we go to symmetric 1353 into 1353 matrix, which is also diagonally dominant, and now this is not from a structured mesh, this we do not use a structured finite difference mesh here, rather we use a finite element mesh to get this. So, the matrix is much more sparsely distributed, we have less zeros and we have non-zeros at further terms, and the regularity is more regular, this is less regular. So, you see that the number of iterations with optimum SOR is 760 for GS. For steepest descent it is order high, it is an order high which is 3723 iteration, and minimum residual it is probably better, which is 33451. So, for even for this particular case, steepest descent or minimum residual did not perform better than GSSOR. Now, we took a case where the matrix does not remain diagonally dominant. It is an asymmetric matrix as well as non-diagonally dominant matrix. GSSOR or Gauss Seidel, that will fail because it is not a diagonally dominant matrix, and we see that we start with some guess value, the solution actually does not converge. Similarly, steepest descent also fails because it is a non-symmetric matrix, it is an asymmetric matrix, and we see that the residual increases with number of iteration, it does not reduce to a smaller value. However, minimum residual can solve it, but the number of iterations are higher, which is 4413. So, what are the observations here are that Gauss Seidel SOR probably performs better than steepest descent or minimum residual in most of the cases if the matrix is diagonally dominant. So, we really cannot get better convergence than what we are getting with optimum over relaxation factor. Steepest descent works only for symmetric matrices. However, the performance is not as good as even close to the Gauss Seidel, is kind of a one order or at least 4 or 5 times more than the Gauss Seidel SOR performance. And minimum residual has a performance similar to steepest descent in most of the cases, but in one particular case when the matrix is non-symmetric and matrix is not diagonally dominant also, minimum residual works, other two methods fail. So, we can utilize minimum residual method for non-symmetric or non-diagonally dominant matrices, but in other cases we will be restricted to use GSSOR because this gives us best performance and will be restricted by the optimum SOR factor, we cannot get better performance. So, two ideas again we cultivate from here. One is that that can we get a method which is much faster than steepest descent and minimum residual. The basic iterative methods cannot be improved more than finding out the best optimum SOR factor, but steepest descent or minimum residual, can they be improved better. And second is that something like a minimum residual algorithm, can it be again developed with much rigor, so that a similar algorithm, but not minimum residual, some algorithm which is similar to that, or some idea of projection based methods, can they be used, so that we can get a matrix solver which works for any matrix, be it non-diagonally dominant, diagonally non-dominant, be it asymmetric, it will still work. However, the number of iterations will be less, and we can see that 1000 by 1000 matrix we can solve in 74 terms. If the matrix is not that structured, at least we can solve the matrix almost in the same number of the same order of the number of rows using GSSOR. So, can we do something with minimum residual or steepest descent type of algorithms? Now, these algorithms limitations we have understood, but can we get better algorithms? So, we will quickly revisit what we are doing in general projection method. We have started with an initial guess x 0 and we find a updated guess x prime, where x prime is x 0 plus another vector k, or combination of few vectors k, and when we update this we keep b minus a x prime, which is the residual perpendicular to another space L. That is the idea of general projection method. This has with choice of k and L, we can get steepest descent, minimum residual, or residue norm algorithms. With different choices of a k and L, we can get these algorithms. So, if I again see what we are doing, we are updating the new guess value from x 0 to x prime plus v y, where v is the basis of k and y are the coefficients multiplied with that. So, we are updating x prime with x 0 plus a vector in the space subspace k, or x prime is x 0 plus delta, we are updating it, so that the residual r 0 is equal to initial residual is r 0 minus b x 0, the new residual r So, the residual will be perpendicular to a space L, and if I have a subspace W which is basis of L, then W's transpose with respect to R 0, this will be 0, and we can do some analysis and find out using this criteria that W is perpendicular to R prime, we can find out y is equal to R prime is the new residual, y is equal to W transpose A V inverse W transpose R 0, and we can update the solution x. This we have discussed in detail when we were discussing the foundation of general projection method. And what we did in this 3 solvers, that we have taken W and V are vectors, that is the space k and the space L, they are one dimensional space. So, there is one vector along W and one vector along V when we try to find it out. So, you can go to the next slide. In one dimensional projection process, precisely that what we have used, k and L are one dimensional spaces in Rn. So, the basis vectors are a single vector, V has a single basis, W has a single basis, and we can find out the alpha is W transpose R 0, which is instead of y, now we have to find out scalar value alpha, which will be multiplied with the vector V, and we will get the updated solution. Now, one question directly comes here, that W k and L were general spaces, were our initial idea, but now we are taking k and L as one dimensional space. So, I have a vector x 0 which is not solution of b minus a x is equal to b. The actual solution of x is equal to b is another vector x prime or x star say. So, x 0 and x star, they has to be related to like x 0. So, my guess is if a x 0 is not is equal to b and I have a x star is equal to b. So, I have to find out x 0 minus x star basically. So, I will start with an x 0 and I will see that how I can relate to x star, and this should belong to some space say k star. Now, when I am assuming that this at any iteration step this is a single dimensional space, I am only going along a vector, and maybe at the next iteration I will take considering another single dimensional space. So, I am going along different single dimensional space till I reach x star. So, this k star is we really cannot ascertain that k star is a single dimensional space. K star is a space where there are multiple dimensions, multiple basis vectors, multiple independent vectors should be there, but in each iteration I am just only covering one basis of that. So, if k star is a very large dimensional space, because if I have 1353 into 1353 matrix, k star can have 1353 basis. So, I will at least need 1353 iterations, and on top of that if I am not going in the right direction, say I went along a vector, I went along another vector, and the next iteration probably I am going along a dependent vector. So, I am not actually approaching all the bases of k star. So, this can in principle increase the number of iterations, because I have to go to a some multi say n is the dimension of or n prime is the dimension of this vector. So, I have to go to an n prime dimensional space, but every time I am only going along a single dimensional space. So, what we will try to see is that we have assumed one dimensionality of k and l for simplicity. Is it restricting the convergence rate, or if we can assume a higher dimensional k and l can get better convergence rate. Can we assume higher dimensional k and l for faster convergence? So, now we should see that what are the implications of taking higher dimensional k and l, and how can we find out basis of higher dimensional k and l. See, we need to find out this basis v and also this basis w before we find out what is alpha and multiply alpha with v, and then we update the solution x prime. So, how can we get a multidimensional space? What will be the basis vectors of a multidimensional k or of a higher dimensional k, and also how can we update the vectors, update the iterations, update it through the iteration. Instead of if it is a single dimensional vector, this is alpha. If it is a higher dimensional vector, the alpha is, this is not a scalar, but rather we will get that x prime is equal to x 0 plus some matrix y into the vector v. We will have some say n prime is the dimension of v, and y is also a matrix with n terms, or y is again like a vector. So, I have to find out y will have number of elements, I have to find out all the elements in y in that case. So, how should we approach the multidimensional k and l? So, I will try to start this discussion in this session, but again and again, because this is has certain amount of abstractness, and also in some cases the mathematical concepts may be little difficult to convey. So, we will revisit this again after we have get certain idea through these sessions. We will again revisit these concepts later. So, what if is k and l has dimension more than 1, x m is equal to x 0 plus k m and b minus x m is perpendicular to L m. Dimension of k and m l, let us assume that they are m in R n. So, instead of k being a single vector v, now I will probably have that k is a vector which is spanned by number of vectors v 1, v 2, v n m, and each of v I is basically a vector in, if I am solving A is n into n and x belongs to R n. So, each of these vector basically belongs to, so this is v I 1, v I 2, v I n. Each of these vectors will belong to real coordinate space n. So, dimension of L and M is m, and x 0 is linearly transformed to an affine space M, and this gives another interesting concept. What is an affine space? So, initially this is the space in which x 0 belonged. Now, we are adding a vector subspace with x 0 and we are getting x m. So, 0 0 does not remain, if 0 0 x 0 is a vector where 0 0 remain to x 0, in x m there is nothing called 0 0, it has been shifted by a vector space k m. So, it is not exactly a vector space because it does not contain the origin right now. We call it an affine space, that is parallel to the vector space where x 0 was belonging. It is a parallel space to that and shifted from origin by the subspace k m. Now, the next question will be that how are the basis vectors for that m dimensional space? K m is an m dimensional subspace, and how will be the basic vectors for that? For that, let us go back to the steepest descent type of algorithm. That is, I have I have residual r is equal to b minus x, and I update my x for any iteration. So, this is like a steepest descent algorithm. Is equal to x k plus alpha k r k. So, x k, instead of shifting it by a vector space, I am just shifting it, I am just adding a vector with a single vector with x k. And what is r k? We can write r k is equal to b minus a x k, r is equal to b minus x. So, I can write here x k is equal plus alpha k b minus a x k, that will give me x k plus 1 is equal to x k plus alpha k alpha k, and I will not put anything here. I can also write that x k, similarly x k is equal to x k minus 1 plus alpha k minus 1 r k minus 1. So, this will be b minus a x k or b minus a x k is equal to b minus x k minus 1 plus alpha k minus 1 r k minus 1, and b minus x k minus 1 is again b minus, sorry, there is an a, b minus a into x k minus 1 plus a into alpha k minus 1. So, this is again r, b minus x k minus 1 is r k minus 1 plus a alpha k minus 1 r k minus 1. So, if I substitute it here, I will get r k minus 1 plus a alpha k minus 1 r k minus 1. I am just substituting a x k here, and this will give me, this is x k plus alpha k r k minus 1 plus alpha k minus 1 a r k minus 1. Now, I can further use the this recursion type of relations, that r k is equal to r k plus 1 plus a alpha k minus r k minus 1 and x k is equal to, again here I can substitute x k is equal to x k minus alpha r k minus 1. So, I will substitute this here, I will also substitute this here, and so that I will finally reach x k minus 1, then I will go to x k minus 2 etcetera, and I will finally reach that x k plus 1. So, after recursions is equal to x 0 plus alpha 1 r 0 plus alpha 2 a r 0 plus alpha 3 a square r 0 or sorry this is r 0 plus so on up to alpha k a to the power, so this is a to the power 0 alpha k minus 1 a to the power k a to the power, so this is alpha k minus 1 and a to the power 1 a to the power k r 0, something like that. So, instead of going through one single iteration, if I can combine all the iterations, I can update x 0 with another vector, and this vector has this vector is combination of several vectors. Combination of r 0 is one vector, a r 0 is one vector, a squared r 0 is one vector, a to the power k r 0 is one vector. So, I am updating it by combining a number of vectors, and if I can find out these coefficients alpha 1 to alpha k, and if I can also form a vector subspace with r 0 a r 0 a square a k r 0, this is basically one iteration which is required. So, if I can find out all the updates using this recursion for steepest descent algorithm, and I can find out the alpha 1, alpha 2, alpha k, then it is a single step which directly takes me from x 0 to x k plus 1, and that is precisely the idea of Krylov subspace method. So, we will find out this space r 0 a r 0 a square r 0 up to a to the power k r 0 for k plus 1 at the update, and then we will find, then we need another method to find out this coefficients, and when we can find out the coefficient, we can directly find out what is x k plus 1. Now, I said like it's from the one dimensional projection process or steepest descent type of algorithm, it looks like a single step, but finding out these vectors, that will take a number of iterations again till we can define this particular space etcetera, and this is what is called Krylov subspace when we formulate a space using r 0 a r 0 a square r 0 and all this. So, we define Krylov subspace as a subspace generated by a n into n matrix and any vector f in R n, which is a m dimensional subspace, and Krylov subspace is called an m dimensional subspace if we go to K m, which is spanned by all the vectors f, a f, a square f up to a to the power m minus 1 f. And these vectors are called near independent spanning sets. If say I have a vector f and I have another vector a f, they can be only linearly dependent if a f is equal to lambda f, that is f is an eigenvector of A. Otherwise, they will be linearly they can be only linearly dependent in that case. This is the only case that they are dependent, that f is an eigenvector of A, otherwise they will be linearly independent. So, if I think of a matrix f, a square f, a m minus 1 f, I can actually go till I have all the independent eigenvectors of M. So, that I can formulate a space where all the vectors are independent to each other. And but if I am exhausted, say f is A is n into n matrix and I go up to M which is equal to, which is greater than n, then I will not find any other independent vector. So, up to a certain value of M we can formulate independent vectors, and that is k 1, k 2, k 3, and this will go up to certain value, say k nu. After that, so k 1 is smaller than k 2, f and a f is a subspace of a f, f a f square f, they are two independent vector. When I add this is another independent vector. When I add a 3 f, I will add another independent vector, and this will probably happen till I got k nu, and then k nu plus 1 will be same as this space, because this spanning space and the, when I am not adding any further independent vector, the space I have already formed will remain constant if I add any dependent vector into that. The span will be constant, because span will be done by the basis, which is the maximum number of independent vectors in that particular set. And when I find out all the independent vectors up to k nu, this the space will be a super space of the previous one. After that I am adding only a dependent vector and the space will not change. Well, so this is, apart from this, this is what is known as a Krylov subspace. And now we will see that how Krylov subspace can be utilized to develop matrix solvers, and from in the next session we will start looking into it. Thank you.